I must apologize at first because I have Parkinson's disease, so I shake a lot. Even when I'm moved or when I'm interested in the subject or when I'm talking about it's worse. But with a guide I prepared, I think it's going to be interesting and even leading on in the presentation. I'm going to talk about the work Newton da Costa and I have been developing for the last 30 years, which has to do with undecidability and incompleteness in the mathematical versions of the empirical sciences. It began with a problem formulated by Maurice Hirsch in 1976. It's the decision problem for chaotic systems. Hirsch asked for some algorithmic criterion to determine, given a dynamical system through its equations, whether it would develop some chaotic behavior. We worked on this question for 5 years, Newton and I. And the answer was somewhat surprising. There is no general algorithm. No matter the definition you have for chaos. The only requirement is that it's not a trivial characterization. That means everything is chaotic or nothing is chaotic. When you can separate between chaotic stuff and non-chaotic stuff, you cannot build a general algorithm to test for chaos. This result we sent it to the International Journal of Theoretical Physics, which published it in 1991, and it deserved a comment by Ian Stewart in Nature before being published. Actually, this follows from a much general result, which is a version within classical analysis of Rice's theorem in computer science. Let me see. Yes, actually, we hadn't noticed that we had actually generalized Rice's theorem in order to decide the chaos thing. And when it became clear, we noticed that it settled several other interesting questions. First, let me give you an idea of how we proceeded in order to reach this generalization of Rice's theorem. As I said, we must have a property which separates the given elements of some sets. which means some elements of that set have this property, and there are other elements that do not have that property. And when you have that, you have a property that is undecidable. In order to separate, to prove, to give an example of an undecidable object and which is related to some undecidable sentence, you need an expression for the halting function. We were really very much surprised because how can I say, we required lots of very weird objects in order to prove this generalization of Rice's theorem. And the chief one was an expression for the halting function in computer science, but not within the language of arithmetic, where it cannot be done. We noticed, however, that if we slightly extend the language, we can have an explicit, actually infinitely many expressions for the halting function. And this allows us to prove several undecidability and incompleteness results. For the incompleteness part, we needed to settle another question, because we had to axiomatize portions of the theory where we were working. And this meant that we had to confront another very interesting and very difficult problem, which was Hilbert's sixth problem, the axiomatization of physics. We have just finished a book which is going to be published by Otávio Bueno's Synthesis collection on Hilbert's sixth problem. We essentially give axiomatics for most of physics. Essentially physics that can be formulated as dynamical systems. And the first moment we confronted this problem was when we were trying to obtain out of the undecidability results we had just obtained for chaos and so on, incompleteness results. That means we were able to exhibit an explicit system which in a given model would turn out to be, say, chaotic, but so that no chaos property could be proved or disproved about it. To give an idea of the halting function, I got this sample from this book of us. Actually, the integrand includes a polynomial, which is the universal Diophantine polynomial, and which is the trick that makes this machinery work. everything is very, I'm just sketching the main steps, but everything is very straightforward. One of the constructions we made for the halting function directly leads to Chaitin's omega number. It was again a surprise because the original formulations were very different and seemed to have no direct connection to Chaitin's omega. But we could go further. We could get other results. For instance, these are two problems in classical mechanics which had been long. For example, the integration problem for the Hamilton-Jacobi equation. The Hamilton-Jacobi equation is one of those equations that summarize everything about the classical mechanical system. Is there a general procedure to find a way of integrating it? Because sometimes it's a very cumbersome animal, so to say, to deal with. No, there is no general procedure. We immediately got those results. And this follows from the fact that you cannot decide whether some mechanical system can be integrated by quadratures. But there is more. All of a sudden, we received in our group a brilliant economist who wanted to get his PhD under our advisorship. I mean Newton's and me as a subsidiary advisor. And we published together, this Marcelo Tsuchi, we published together a few papers. One of them, which is very much referred to in the literature of economics, of neoclassical economics, which is, for a competitive market, there is no procedure to decide whether we have equilibrium prices or not in the general case. This is very surprising because there is some kind of dogma that the market settles everything. The market may set, I doubt, I have great doubt about the efficiency of the market. But even if the market were able to settle everything, we would never, in the general case, be able to determine whether that position, that equilibrium reached by the economic market, where the true equilibrium or just long transition with the appearance of equilibrium. And there is more. This is a recent result which is related to these results and which we obtained almost by chance. Let S be a theory. This is in computer science, and it has to do with complexity issues. Let S be a theory, a nice theory, recursively enumerable set of theorems, and includes Peano arithmetic, and is very well behaved. Then, and let S prime be its sigma prime extension. S prime proves that there is no proof for S for P different from NP within S. This doesn't mean that there isn't such a proof. It only shows that the theory isn't seen from the outside, isn't strong enough to find that. I think that's most intriguing, and also it shows the depth. It's an example of a result that shows the depth of complexity issues, and in particular the P versus NP problem in computer science.
Thank you, Professor.
Sorry for the shaking, but I must say I'm really very moved by the interest that these problems awake in me. And thank you very much for your patience.
Please, is there any question? Yes?
Three small questions. In the first part of your talk, you mentioned languages to express the working problem, which are close to arithmetic. Did you mean objective?
Actually, we do not start from Chaikin's constructions. We reached those constructions at the end. The thing happened like that. I was at Stanford, and Pat Sulpice learning about my interests in Pat Sulpice. I think it's not. Okay. So, Pat Sulpice suggested that I take a look at Daniel Richardson's 1961 and 68 paper on the computational. Well, there's I don't quite recall its title, but it's a paper by Daniel Richardson, which when I browsed through the paper, I noticed that it implied that ergodic systems were undecidable. It's a direct result. Then a few more transformations led to the construction of the Hawking function. Kaiser had conjectured, had mentioned the possibility of having something like that in a 1973 or 4 paper, which was published in a collection of essays in book form. And Scarperini, Bruno Scarperini, referred to this same construction in a paper published in 1962. Well, then we started to look for other presentations of the Hawking function. And there is one which amounts formally It's just an infinite series. It leads directly, it directly implies Chaitin's omega number. But we didn't, I knew Chaitin's construction. I have already met him at Santa Fe and was very happy to connect in such an easy way our results with his. I like Chaitin a lot, and I keep telling him that his work is a constant inspiration for my own work. And by the way, there is a very interesting romance by Arturo Sangalli, Pythagoras' Revenge, where he announces a theorem by a fictitious mathematician, Norman Thorpe, which says that undecidability and incompleteness are everywhere in the domain of mathematics. And I gave a proof for that result. It's going to appear in a book we prepared to honor Chaitin's 70th birthday in a paper whose title is, in Italian, Selva Selvaggia, which means savage jungle. It's a reference to a verse by Dante. And it intends to be an apt depiction of how mathematics is. Mathematics is not an ordered landscape. It's a brutal, savage landscape, jungle.
We have time for one more small question.
I have a large question. Let me put it very briefly. You know, these are very beautiful mathematical results, which I love very much, this sort of thing. My question is whether, you know, the applications to neoclassical economics or other are also of some more practical, I would say, substantial use. Because, you know, the fact that there are limitations, there is no algorithm doing something for everything, for every possible whatever, is one thing. But the other thing that maybe for all those practically important issues, there are some algorithms. So the question is whether economists or other could use the result, as far as you know, or could use it in a way that would be constructive for them and not just mathematical. Which is not saying that this is unimportant. It is important, but still, it's not the same as practical,
You're right. And I must say, it's a problem of mine. I approached it from the side of mathematics, the beauty of the mathematical result. I'm going to refer to another result, which is in a paper of mine called A Beautiful Theorem. It's based on a theorem by Phil Mayman, who is a neoclassical mathematical economist. And he says that there are efficient markets if and only if P equals NP. It's beautiful because it connects two different areas: complexity theory and neoclassical economics. And the way it was formulated by Mayman, it was really difficult to handle, to use. But we made technical mathematical hypothesis, made a few changes, and managed to get a workable version of this theorem, which is they are almost efficient markets if and only if P equals NP. And there is a reasonable definition for almost sufficient, because the problem, the technical problem lies in the formulation of efficient markets. But I must say it's my fault. I approached it from the side of the beauty of mathematics. I wasn't really interested. Just to conclude, about 1 week ago, I had dinner with a long-time friend who was chairman of the Brazilian Federal Reserve. And he questioned me about these results, exactly as you are doing now. And I said, it's my fault. I like the beauty of it. It's abstract music, it's chamber music.
Thank you, Professor. It has been an honor to have you here. So please.
Thank you very much, and thank you very much.